Okay.
Is it okay, sir?
Okay, everything's okay. Please go ahead.
Okay. First of all, good evening. Myself, Mohd Vasiulla. I am from Jamia Millia Islamia, New Delhi, India. My topic is application of mixed generalized quasi-Einstein space-time in general relativity. These are overview of my paper. First one is introduction, and second one is mixed generalized quasi-Einstein manifold with the recurrent fields generators. And third one is mixed generalized quasi-Einstein manifold with the concurrent vector fields generators. And fourth one is mixed generalized quasi-Einstein manifold with Einstein's field equation. And last one is mixed generalized quasi-Einstein space-time admitting a space matter tensor. Introduction. An Einstein manifold is a Riemannian or pseudo-Riemannian manifold whose Ricci tensor, which is denoted by Ric of type 02, is non-zero and proportional to the metric tensor. Einstein manifold form a natural subclass of various classes of Riemannian or semi-Riemannian or pseudo-Riemannian manifold by a curvature condition imposed on their Ricci tensor. Also, the Einstein manifold play a very important role in geometry as well as in general theory of relativity. MC Chaggi and RG in 2000 introduced and studied the quasi-Einstein manifold. An unflat and dimensional Riemannian manifold MNG and its dimension, which is greater than 2, is said to be a quasi-Einstein manifold if its Ricci tensor Ric of type 02 is non-zero and satisfy the following condition: Ric xy equal to agxy plus baxay, where a, b are scalar and a is non-zero one form, which is defined by gx rho equal to ax and g rho equal to a rho equal to 1. Rho is vector field called the of the manifold, and one form is also called the associated one form. And from one, it follows that every Einstein manifold is a quasi-Einstein and is denoted by QEN. A non-flat Riemannian manifold MNG is greater than n is greater than or equal to 2 is said to be a generalized quasi-Einstein manifold if its Ricci tensor Ric of type 02 is non-zero and satisfies the following condition, which is 3, where ABC and AB are non-zero one form associated with the two orthogonal unit vectors rho and sigma are defined by 4. And generalized quasi-Einstein manifold is denoted by GQEN. A. Bhattacharya and Tide in 2007 introduced the notion of mixed generalized quasi-Einstein manifold. A non-flat Riemannian manifold is said to be a mixed generalized quasi-Einstein manifold and denoted by MQEN if its Ricci tensor Ric of type 02 is non-zero and satisfy the following condition, which is given by 5, where ABCD are non-zero scalar and A, B are non-zero one form, which is defined by 6. Quasi-Einstein manifold has importance in cosmology and general theory of relativity. Yusude H.K. Said and in 2021 studied about mixed generalized quasi-Einstein work product manifold, and in S. Fan B. Bhattacharya they are also discussed on multiplied work products quasi-Einstein manifold with quarter symmetric connection. After studying this paper, we are investigated to study about mixed generalized quasi-Einstein spacetime. In equation number 5, putting x equal to y equal to ai an orthogonal basis of tangent space at each point on the manifold and taking summation over I, and I is between 1 and n, and contracting over equation 6, we get the equation number 7 are equal to na plus b plus c, and contraction is the reduces the rank of the tensor where R is the scalar curvature of the manifold. A space-time is a time-oriented four-dimensional manifold M4 with Lagrange metric whose signature is plus 2 minus. A Lagrangian four-dimensional manifold is said to be a mixed generalized cosiness space-time with the generator rho as the unit time-like vector field if it non-zero Ricci tensor of type 02 satisfies the equation 9. If rho is the time-like unit vector, then we say that the mixed generalized cosiness manifold is said to be mixed generalized cosiness in space-time. And A and B, two non-zero uniform such that rho sigma is the heat flux vector field perpendicular to the velocity vector field rho. And therefore, for any x, we have equation number 8. Further, we know that if the Riemann curvature K bar of type 04 has the form is 9, then manifold is said to be a constant curvature K. The generalization of this manifold is the manifold of quasi-constant curvature. And in this case, the curvature tensor has the following form, which is 10, where gk xyzw equal to k bar xyzw, and k is the curvature tensor of type 13, and a b are scalar function of which b non-zero and is non-zero one form defined by 11. A Bhattacharya and Pide in 2007 defined a new type of quasi-constant curvature, which is called the mixed generalized quasi-constant curvature, defined as follow, which is given 12, where f1 f2 are scalars of which f1 to f4 are non-zero and a comma b are two non-zero form defined earlier, rho comma sigma being two unit vector fields such that rho sigma is equal to 0. Such manifold is denoted by MGQCN. Next section is mixed generalized cosinus manifold with the recurrent vector fields generators. Let us consider the generator rho and sigma corresponding to the associated one form A and B are recurrent. Then we have, and where eta and psi are non-zero one forms. A non-flat Riemannian or semi-Riemannian manifold MNG n is greater than 2 is said to be a Ricci recurrent manifold if its Ricci tensor Ric of type 02 is non-zero and satisfy the following condition. Is question number 13. Alpha is non-zero one form, and we know that question number 14. And comparing 14 and 13, if follows it, we get 15, and using 5 in 15, we get equation number 16. If we put y equal to z equal to in previous equation 16, we obtain the equation 17. Since dx rho equal to 0, rho is the, and using 6 in 17, we have equation number of 18. So dx sigma equal to 0 if and only if x a plus b minus alpha x a plus b equal to 0 implies that either dx sigma is perpendicular to rho or sigma is parallel vector field. Again, we putting y equal to z equal to sigma in question number 16, we have 19, and since b dx sigma equal to 0 and using equation 6 in 19, we have 20. So b dx rho equal to 0 if and only if x a plus b minus alpha x a plus b equal to 0 implies that either dx rho is perpendicular to sigma or rho is parallel vector field. Hence, we can state the following theorem. If mixed generalized quasi-Einstein manifold is recurrent, then x a plus b minus alpha x a plus b equal to 0 if and only if either dx sigma is perpendicular to rho or sigma is parallel vector field. And second, x a plus b minus alpha x a plus b equal to 0 if and only if either dx rho is perpendicular to sigma or rho is a parallel vector field. Next one is a vector field phi is said to be concurrent if it satisfies the following conditions. Which is given 21 where xi is constant. Consider the generator rho and sigma corresponding to associated one form and B are concurrent. Then we have 22 and 23. Lambda and mu are non-zero constant. And taking the derivative of equation number 5 with respect to z, we obtain equation number 24, and using 22 and 23 in 24, it follows that which is 25. And now contraction of 25 over x and y, we have 26, and from 7 we get r equal to n a plus b plus c, and r is a scalar curvature since a or b in real number, therefore derivative of scalar curvature is 0 for all x, and using drx is equal to 0 in 26, we get equation number 28. By virtue of 28 in 25 in 5, we have equation 29, which is a quasi-Einstein manifold. Hence we can state the following theorem. If the associated vector fields of a mixed generalized quasi-Einstein manifold are concurrent vector fields and the associated scalar are constants, then manifold reduces to a quasi-Einstein manifold. Next section is mixed generalized quasi-Einstein manifold with Einstein's field equation. The Einstein field equation is xy minus r by 2 gxy plus lambda gxy equal to kappa txy. R and k and lambda are scalar and gravitational constant, and lambda is cosmological constant. If lambda equal to 0 in 30, we get the equation number 31, and it is called the Einstein field equation without cosmological constant. Using 6 in 31, it follows that it is 32, and covariant, taking the covariant derivative of equation 32 with respect to z, and we give 10 33.
Professor, please summarize your presentation.
Okay, sir.
Couple of minutes left.
Okay.
Thank you.
Hence we state the following theorem. If the associated one form A and B in a mixed generalized quasi-Einstein manifold are covariant constant, then the energy momentum is also covariant constant. Next section is mixed generalized quasi-Einstein space-time admitting space matter tensor. To introduce the space matter T bar of type 04, the space matter tensor is defined as follows, which is 34, where P is the space matter tensor of type 04 and K bar is curvature tensor of type 04. T is the energy momentum tensor of type 02, and kappa is the gravitational constant, nu is the energy density. And G and G, which product T are defined as 35 and 36 for all x, y, z. In Chi-M is the set of all differential vector fields using 35 and 36. In 34, it follows that 37. If P bar equal to 0 in 37, we get 38. And using 5 in 31, we obtain 39. From 38 and 39, we get 40. Where F1 equal to the F2 minus B by 2 and X3, F4. Hence, we can state the following theorem. A mixed generalized quasi-Einstein space-time satisfying Einstein's field equation with 0 space matter tensor is mixed generalized quasi-constant. Quasi-constant curvature is space-time. Next, we investigate the existence of sufficient condition under which mixed generalized quasi-Einstein space-time can be divergence-free space matter tensor. from for derivative of curvature, scalar curvature is equal to 0, and using in 37 we obtain 41 and 42. Hence we can state the following theorem: the energy density is constant in a mixed general cosiness space-time, satisfying the Einstein's field equation with divergence free space matter tensor. Now using 5 in 42 we get 43. Consider the equation are constant, and general rho is parallel vector field dx, that is dx rho equal to 0. Therefore we get 44, and in view of we derive 45 using 44 and 45 in 5 we obtain divergence p x y z equal to 0, and hence we can state the following theorem: if the energy density are associated with scalar are constant in a mixed cosinus space-time with parallel vector field rho satisfying Einstein field equation, then the space and matter tensor divergence is vanished. These are references of my paper. And last is thank you, sir.
Thank you, Professor Vasiulla. Dear attendees, is there any question or comments? Please can use question answer section.